Good afternoon, everyone. Let us start this lab session. So this is the experiment number 1. The title is Study the longitudinal vibration of the helical spring and the natural frequency calculation for the spring mass system. So aim is to determine the natural frequency, that is omega n, of the given spring mass system. So in that first case is when the springs are connected in the parallel, and second is the series arrangement. So requirement, so then dead weights, fixed support, scale, and the stopwatch. So this is the schematic diagram. So in this setup, so we have the single spring. It is not series or parallel arrangement. So this is the coil helical spring. Then this is the fixed support. This is the scale to measure the deformation. And this is the dead weight. So this weight, so it is a standard weight of 1 kg, 2 kg. Okay, so this is the physical setup. So when we will conduct this experiment, so there are two parts. So first is to determine the spring constant, that is called as a K, of the given spring, and second is to determine the natural frequency. Of given spring mass system. Okay, so simultaneously we will study what is meaning of longitudinal vibration. Okay, so during the third module, that is a free vibration, free undamped vibration. So I have explained what is meaning of longitudinal vibration. So this is the simple spring mass system. And this is the axis of that system. And suppose this dotted line, it represents the static equilibrium. Okay, that is the mean position. So from this mean position, if you provide a small displacement x to the mass, then this mass will oscillate about this mean line, okay, continuously, because there is no damper in the system. Okay, so this oscillation of the mass, they are along this vertical axis. Okay, so oscillation direction is parallel to the axis of the system, and this is called as a longitudinal vibration. Okay, so for this longitudinal vibration of a simple spring mass system, we have to find out what is the natural frequency experimentally. Okay, and at the same time, we will find out this frequency by theoretical formula. So theoretically, for this system, suppose the stiffness is K and this is the mass of the system. Then we have the standard formula omega n, this is equal to square root K upon m. And unit is radian per second. So theoretically, we can find out omega n by this formula. Just we should know the value of K and the mass connected. Okay. So initially for this experiment, this spring constant is unknown. We don't know what is the value of K. just a spring is given, that is a coil spring is given. Okay, so this is the given spring, and for this spring we have to find out what is the K value. The stiffness or spring constant, unit will be Newton per meter. So this is the first step, and in the second step we will perform the experiment for the natural frequency calculation. So how to find out the K value experimentally? So for experimental calculation of the stiffness, so we will take this spring and connect this spring with the fixed support. Okay. Now from this fixed support, you should measure the free length. So let us take this free length as a capital L or L1. So this is the free length or undeformed length. Okay. So after connecting the spring with the fixed support, okay, that is a stand, we should measure this L1 and then connect the mass. So it is the known weight. Okay. Now because of this weight, this spring, it will undergo some deformation, that is a static deformation. So there is a deformation. And at this position, after this static deformation, system will remain stationary. It is not oscillating. Okay. So this static deformation, you have to measure this complete length again. So this is a L2. Okay. And then find out this difference. So this is the delta, which is L2 minus L1. Okay. So by measuring this delta, you can find out the unknown value K, that is the stiffness of the given spring. So how to find out this? For that, we should know this relation. Spring force Fk, it is equal to spring constant into its deformation. Okay, now for this setup, what is the spring force? It is nothing but the weight force which is acting on this spring. Okay, so this weight W, this is equal to K into this deformation is nothing but this delta, and this weight, this is mg, which is a mass connected to the system. So this is K into delta, and K is equal to mg upon delta. So by using this formula, you can find out the spring constant experimentally. Okay. So there is another procedure to find out the spring constant, which is a theoretical procedure. But for this experiment, we will only calculate the spring constant by experimental procedure. Okay. So we have to use this formula. So let us see, when we add the mass m to the undeformed spring, then this deformation, so there will be some deformation, that is static deformation. So you can observe in the animation. So this is the static deformation. So at this static deformation, this system is non-oscillatory. It is at the rest position only. So we have to measure this static deformation with respect to its undeformed length. And by putting this value in this equation, you can calculate the value of K. So this is the observation table to calculate the spring constant or the spring stiffness. So you can note down this observation table. So here first column, it is the weight attached. So this is the W. Second is the deformation of the spring. So it is a L2 minus L1. And take this value in terms of meter only. Next column is formula K is equal to F upon X. This is a Newton per meter. So actually, this weight, so basically it is a mass in kg, and you should convert this mass in this formula so that we will get the force value. So you should multiply by 9.81, and then you should calculate the mean value. So here K mean is equal to K1 plus K2 plus K3 upon 3. So we will repeat the experiment so that we will get the accurate value for the stiffness of that spring. So weight attached. So we will connect the weight 1 kg, 2 kg and 3 kg. So these are the known values of the weight. For each weight for the same spring, we will measure what is the deformation. So as we are increasing the weight, we will get the increasing value for the deformation. Okay. So put this value of deformation in the formula of K. So here your K1 value. So actually K1 is nothing but the W upon X. So W will be 1 into 9.81. And you should measure this deformation. So let's take this as a X1. Similarly for K2, this is 2 into 9.81. Put the value of X2. So this value. And K3, this is 3 into 9.81 upon X3. Okay. And then find out the K mean, which is a K1 plus K2 plus K3 upon 3. Okay, so let us see the experimental setup. So actually we are going to conduct this experiment virtually in the Inventor software. So when you conduct this experiment physically in the laboratory, you will have the similar setup. So this is the stand. So it will give the fixed support. Okay. So this is the fixed end for the spring. This is the moving end where we will connect the known weight, that is mass M1, M2, M3. Okay. And this is the scale in order to measure the deformation of the spring. So the scale is connected to the fixed support. Okay. So initial experiment is we should find out the spring stiffness. Okay, so this is the given spring. So this is helical spring. Now I have connected this spring with the fixed support, and we want to measure what is the spring constant, that is the spring stiffness. Okay, so to measure the spring constant, we should connect a known weight to the second end of the spring. Okay, and after that we should measure the deformation. So initially I have connected the known weight of 3 kg. So in the observation table, you enter the value for mass as a 3 kg. So initially its undeformed length, so you can observe here. So undeformed length for that spring is 32 centimeter. Okay. Now at the 32 centimeter, which is the undeformed length, we have attached a known weight, which is a 3 kg. Okay. So I have just written here W. So actually it is a 3 kg. So now I will simulate. So you can observe the static deformation because of the 3 kg. So just observe here, this pointer, it will move in the downward direction. So you can observe here, there is a permanent deformation up to 35 centimeter. Okay. And system, that is a mass, it remains stationary at this position only after static deformation. So we should find out what is a static deformation. So you can observe here, there is static deformation from 32 centimeter to 35 centimeter. Okay. So it is 35.5 something. So difference is, it is a 3 point. So it is a 3.55, that is a 35.5 mm. Okay. So in the deformation column, you should write 35.5 mm and convert this into meter. So in the observation table, you can see here. So this is 3 kg. Okay. And this deformation, this is 35.5 millimeter. Okay. So afterwards, you can convert this in terms of meter. Just multiply by 10 raised to minus 3. So it is point not. Sorry, this is not 35.5. This is 30.5. So it is 0.0305 meter. Okay. And now put this value. So K3 is equal to 3 kg into 9.81. So this is a Newton upon X3 value. And you can find out the K3. So K3 is 981 Newton per meter. Just check this value. Similarly, you can repeat the experiment so that we can find out the exact value. So take the weight 2 kg and 1 kg. So I will change the weight now. So now I am selecting the weight as a 2 kg. So its Newton will be 19.62. Okay, so now let us check the deformation. Now here weight is 2 kg. So undeformed length is same. It is 32 centimeter. So now you can observe there is a reduction in the static deformation as we are reducing the weight. So the system is settled at 34 centimeter. Okay, so we should take the deformation as a 2 centimeter or 20 mm. So the second reading, this is 20 mm. So it is 0.02 meter. Put this value here and get the value of K2. So your K2 will be it is 981. Okay. And similarly, you can have the value when we are selecting the 1 kg as a weight. Okay. So as we are conducting this experiment in the software, so we are getting the exact value for all 3 readings. Okay. But physically, that is when you are conducting this experiment in the laboratory, you may get the variation in the result K1, K2, and K3. Okay. So take the mean value. So mean is same. It is 981 Newton per meter. Okay. So this is the first part to find out the unknown value of the spring stiffness. So theoretically, so this is the experimental procedure to find out the K value. Even you can calculate the value by theoretical formula. So you can note down this formula if you want to find out the K value theoretically. So K is equal to G into D raised to 4 upon 8D cube and into Na. Okay. So here G, this is the modulus of rigidity. For this spring material. Then the Na value, this is the number of active coils. So actually this is G DO raised to 4 and upon 8D I cube into Na. So DO is the outer diameter for the coil. And Di, this is equal to DO minus small d. So actually small d, this is the coil diameter. Okay. So if you take the cross section, so if you cut this, so you can observe this structure. Okay. So this is the outer diameter, and this is the inner diameter. And for this portion, so this is the coil diameter. And here the number of active coils. So Na means when we take the spring, this first and the last coil, they are undeformed. Okay. So the deformable coils, they are nothing but the active coils. So you can observe here, actually there are 10 coils in this spring. Okay. But number of active coils we should take as a 8, because this coil, it is connected with the mass, and this coil, it is connected to the fixed support. Okay, so there will not be any deformation of the first and last coil. So remaining coils, they will undergo the deformation. Okay, so we should consider the active coil as a 8. Okay, so this is theoretical formula to find out the spring stiffness. So for that, we should know the value of modulus of rigidity of the spring material. Now the second part here in the experiment is natural frequency calculation. Okay. So for the natural frequency calculation, we need to oscillate the system, and we will measure the oscillations. That is a time period for the oscillation by using a stopwatch. So this is the spring mass system. And just imagine we have connected 1 kg mass. Okay. So for 1 kg mass, we will give the initial displacement. Okay. That means we are supplying the force only at the initial condition. Okay. Because of this initial force, so we should provide some initial force. I will write here as a Fi. Okay. So there will be some deformation. So mass will get displaced. So that displacement is nothing but x. Okay. So here x is not permanent deformation. So after this initial displacement, we will release this force. So Fi value will be 0 after initial displacement. So as the Fi value becomes 0, then system or mass has tendency to oscillate because of the inertia forces and the spring force. Okay. And then it will oscillate up and down about the mean position. So for this oscillation, we should measure what is the time period. That is the time required to complete the one oscillation. Okay. So to measure this time period, actually, we cannot measure time exactly for one oscillation. Okay. So we should measure the time for 10 oscillations. So here I have written total time for 10 oscillation. So it is written as a small t. We will conduct experiment only for 1 kg, and stiffness we have calculated as a 981 Newton per meter. If you take the value m as a 2 kg, then total system will change. It will have different natural frequency. Okay, because natural frequency, it depends on k value and m value. If you change mass or k, its omega n, it will change. So this experiment, it is only conducted for mass m is equal to 1 kg and k is equal to 981 Newton per meter. So we will repeat this experiment so that we can find out the exact value of time. Okay, so we can minimize the measurement error in the time. So first, oscillate the system and find out time for 10 oscillation. Repeat the same experiment and find out the time. Then to calculate the time period, we should divide this total time by 10 oscillation. So we can get the time period. Okay. So T1, this is T2, and this is T3. So ideally we should get the same time t1, t2 and t3, but due to measurement error we may get the variation, and then find out the omega n. So this is omega n1, this is a 2 pi upon t1. Calculate the omega n2 and omega n3. So as there is variation in the time, we will get the variation in the natural frequency and then take the mean value. This is the omega n. Okay, so it is a ratio of omega n1 omega n2 plus omega n3 upon 3. So this is the final value for the natural frequency. So this is experimental procedure to find out the natural frequency. Okay, so take the spring mass system, then give initial displacement, then remove the force after initial displacement, and let the system oscillate for a specific time duration. Okay, so for 10 oscillation, measure the time period or time, find out the time period, and then find out the omega n by formula 2 pi upon t. Okay, because omega n we cannot find out directly by measuring. Okay, so for that we should measure the time period, and by using this formula 2 pi upon t we can find out the natural frequency in rad per second. And then we have to compare this equation, this value with the theoretical value. So omega n theoretical value is square root k upon m. So put the value 981 and mass is 1 kg and find out this value. So this is equal to 31